Hi everybody, my name is Liang Huang from Baidu Research USA and Oregon State University. I'm very glad to give this talk at CVPR 2021, and I would like to thank the program chairs, David, Georgia, Ray Gontin, and Jenny for inviting me to give this invited talk. I'm actually humbled by this invitation because I'm not a CV person. I'm a computational linguist by training, which means I do NLP. And also recently in the pandemic, I've been doing more and more computational biology work. But really, I haven't published any paper at CVPR, ICCV. So so I was a bit worried that maybe this is not of interest to the CVPR audience. But they convinced me that CVPR people love NLP stuff, and so I'm here to give this talk about simultaneous translation. And I hope you'll like it. This talk is based on a keynote speech at ACO 2019, which I gave a couple of years ago, but with a lot of recent results added. So I would like to thank my students, co-authors, and collaborators, first of all, because they did all the work and I did all the talking. And before I talk about simultaneous translation for machines, I would like to first give you some background about simultaneous interpretation for humans, for human interpreters. But even before that, there is something called consecutive interpretation, which is even easier, where when the two presidents meet, Xi Jinping would say a sentence, and the interpreter will translate it into English, and then Trump will respond, and then another interpreter would translate back to Chinese. So that's great, but that's easy, but it costs a lot of time. A 1 hour speech, 1 hour talk between you and me can take them at least 2 hours. So this multiplicative latency by times 2 is very costly, especially for people like presidents. Instead, since the 1945 Nuremberg trials, people have been doing a much more efficient interpretation called simultaneous interpretation, where you would start to interpret or translate only about 3 seconds into the source speech, and finish only about 3 seconds after they finish. So it's much more faster and takes much less time. And you can see that when President Xi Jinping and President Trump meet again, somewhere maybe in Florida, the two sides actually use simultaneous interpretation. This is evident from the fact that the US side is all listening to the headset while Xi Jinping speaks. Right? So somebody's doing the job actually in another room, not in the scene, except for one person. Can you see him? Yeah, President Trump. Yeah, he is not listening to the headset while Xi Jinping speaks. He's either pretending that he understands Chinese, or he just doesn't care whatever Xi Jinping wants to say. That's typical of Trump. But yeah, everybody else is listening to simultaneous interpretation. And here's another example at United Nations when Chinese speech is translated on flight into English.
We also thank UK for presiding over the Affairs and Security Council.
You can see that the Chinese speech is only 3 seconds ahead of English translation, right? So this is great, but it's extremely difficult to do. Our brains are not made for that kind of simultaneous production and comprehension in 2 different channels together, right? So on one side, you're listening to Chinese speech, and then you're producing English translation at the same time. You just cannot do that, right? Your CPU will burn in your brain. So as a result, there are very, very few people worldwide who can do this job. So there are only 3,000 members of this, AIIC, Association of Conference Interpreters, and outside this, there are people outside of this AIIC, but together there are only about 10,000 people worldwide who can do this job today. And each one of them can only sustain for 15 to 20 minutes, and after which they have to switch off. So at United Nations, they work in groups of 3. Or at least 2. You cannot do the job yourself. And the best of them can only recover about 60% of the source material. The other 40% they have just to throw away, because if they want to translate every single detail of the source speech, they will lag behind too much, and more from the source speech, and then their working memory will just explode, and that's just a disaster. And that happened actually once in the United Nations when Gaddafi made a speech, and his interpreter was just collapsed to the floor. Okay, so here there is a trade-off between latency and quality, And if we can do consecutive interpretation, as I said on previous slide, we have to wait at least for for 1 sentence delay. And written translation is even higher latency, but quality is very good. And full sentence machine translation, as we all know, is very close to human quality in some well-known languages like English and Spanish. And you can see the Spanish translation on Google Translate is so good. The English-Chinese translation on Baidu Translate are also so good. But simultaneous interpretation is much faster in speed, only 3 seconds, and the quality is very low, very, very bad. And on the other extreme, on the other side of the spectrum, if you can do extremely low latency, word-by-word translation for, let's say, Italian-Spanish or Spanish-Portuguese, yeah, it works for those very closely related languages, but for other language pairs, word-by-word translation doesn't work at all. You would get a very low quality output. You would get like word salads in the target language, like get Chinese word-ordered English, which people cannot understand, right? So there's a trade-off curve, right? What we want to do is to push towards the top left corner, where you would have low latency and high quality. But previous work in simultaneous translation, before we jumped into this field, have very bad latency. Actually, quality is not very good either. But the more of the problem is actually in the latency, because for the user, like if you guys hear me speak right now using simultaneous interpretation or simultaneous translation, you would actually care more about latency, because if latency is too high, then you go out of sync with me. I was already talking on the next slide. You were still listening to this translation of the previous slide. That's awful, right? So we want something that is controllable latency, like 3 seconds delay, just like human interpretation, but much higher quality, right? And this is considered one of the holy grails of AI, one of the hardest problems of AI. And we already know that sequence to sequence, which is very good for full sentence translation, is not good at all for simultaneous translation. And we need fundamentally new ideas, fundamentally new frameworks to tackle this problem, which both the source and target sides are growing simultaneously. And towards the end of this talk, I'll be talking about a whole pipeline from source speech to target speech, speech to speech. But for now, I will be focusing more on the text-to-text part to demonstrate the algorithms. So yeah, this is the outline, and the first part will be about our breakthrough in 2018, and as a result, after the breakthrough, we kind of rejuvenated interest in this field, and the number of researchers in this field is growing exponentially. Okay, so before our work, simultaneous translation is still done in full sentence translation. So really, there's no simultaneous translation per se, and you would wait until the end of a sentence to start translating it. The latency is often more than 10 seconds. So you can see this video. You can see the English translation is lagging behind. It's not moving at all, right? So you would wait until the source Chinese speech finishes the sentence. And then the English translation starts to go in. That's too slow. That's really too slow. After our work at the end of November 2018, our work is not just written into a paper, but also made into the product within Baidu. So you can see the demo. You can see both English and Chinese are growing at the same time, constantly. So there's no like 1 sentence delay, and the latency is back to about 3 seconds, which is very similar to simultaneous interpreters. And that's a great progress. And how did we do it? Well, as I said, we need fundamentally new ideas beyond sequence to sequence, right? So let's look at the main challenge that we are facing for machines to do this job. As I said, for humans to do this job, we have lots of other constraints like working memory, like the simultaneous production and the comprehension, all these kind of tasks which were not made for our brains. Those are the difficulties for human interpreters. But for machines, the major difficulty is the word order difference, which is also a difficulty for human interpreters. But for machines, that's probably the most important one, because machines don't care about working memory. It has infinite working memory and so on and so forth. And it can also multitask. That's not a problem at all. But What are the difference between the source and target language? That's just unsolvable for machines. If you translate from German to English or Japanese to Chinese, you would go from a subject-object-verb language, which we call SOV word order, to an SVO or subject-verb-object word order, right? And this is an example from German to English. As you all know, German verbs are often at the end of the sentence. Ich bin mit dem Zug taking the train nach Ulm gefahren, which is the verb traveled, only arrives at the very end. And if you don't anticipate, you have to wait until the end of the sentence. There's a huge delay here in the middle of the sentence. And that's why there's a famous joke in not the United Nations, but European Union, that is, whenever the German speaker speaks, the interpreter will just stay there doing nothing. And people would ask her, well, why are you not doing any translation at all? And she would say, I'm waiting for the German verb. No, German verb wouldn't arrive until 10 seconds later, right? So that caused a huge problem. But human interpreters actually, in this situation, they routinely anticipate and make predictions of the German verb. And for example, with the train, you already have the dem Zug with the train. You know that in this context, it's 99%, you can say something like went or traveled, right? It's fine. Even if it's not exactly went or traveled, it's something quite similar to that. So they do that kind of anticipation all the time. And let's look at another example from Chinese to English. So Bush president in Moscow with Russian President Putin meet. The verb, Chinese verb, also comes at the very end. But on the English side, you would prefer to say President Bush meets with Russian President blah, blah, blah. If you don't anticipate, you have to wait until the very end. But human interpreters in this context could safely say, oh, President Bush meets. And after you hear Bush president in Moscow, President Bush meets with Russian president. Why? Because what can he do, right? He's President Bush, not President Trump. What can he do in Moscow? He cannot play golf. He'd better just meet with Putin, right? So in this context, a trained human interpreter would often just very boldly just predict the verb to be meets, right? So that's very good. We want the machine to be as intelligent as that. So here comes our idea, which is called prefix to prefix, which goes beyond sequence to sequence. As we all know, sequence to sequence is okay for full sentence translation, where you would encode the whole sentence, the whole source sentence, before outputting the first target word, right? So in other words, each yi on the target side is dependent on the whole source sentence plus the prefix, which you all just generated on the target side. So that's called sequence. It's ill-suited for simultaneous translation. For simultaneous translation, you don't want to wait until the end of the sentence, right? You want to wait for two words and then start generate the first target word, and then wait for the third word and generate the second, and so on and so forth. You want your target to be only like k words behind the source. Here, k is 2 in this case. So in other words, your yi should be conditioned upon not the whole sentence, x1 to xn, but the prefix of the sentence, x1 to xi k plus I plus k minus 1, and the prefix on the y side, which is the same as sequence to sequence. So the difference really is on the source side. I don't use the whole sentence, I only use the prefix. So that's why it's called prefix to prefix. And weight k is a special case of prefix to prefix. In general, prefix to prefix, it's not just I plus k, it can be any monotonic non-decreasing function. But for this talk, we just demonstrate weight k, right? So if you decode this way, you would easily get a controllable latency, because if you just want k to be larger, you can have larger latency. If you want faster policy, you can just set k to be smaller, right? But more importantly, think about if you train the model this way, you take this p of yi, this conditional probability, as the last function, not instead of this one, then you suddenly get implicit anticipation on the target side. It's just like we say human interpreters are also trained this way. During their training, they know that Bush president in Moscow, the next verb must be meets, right? So our system being trained using this last function on a lot of training data on the machine translation parallel text would also realize that actually, whenever you have whatever present in whatever capital city, the next verb is very likely to be means. Of course, you can make a mistake, but human interpreters make mistakes all the time. That's fine. That's just life in this very difficult business, right? So here's our research demo.
江泽民对法国总统的来华访问表示感谢。
You can see the express appreciation part is anticipated long before it's actually revealed on the short side. This is again because the training data contains a lot of some president to some other country's president express gratitude. So whenever you hear Jiang Zemin or whatever leaders to some president, some foreign presidents, you would immediately say Jiang Zemin expressed his appreciation or gratitude. It's 99.9% correct, right? So let's summarize so far. So the prefix-to-prefix framework that we proposed is the first such framework that is tailored to simultaneity, and is a very good fit for simultaneous translation, which is incremental on both sides. It deviates from sequence to sequence, and it's a fundamentally new model. Even though the change looks very small, it's actually philosophically quite different. And the result of this training in such a way is the first genuinely simultaneous translation model rather than using a full sentence translation model as in all previous work. And it's very easy to train, very scalable and repeatable, and quickly become the only standard approach, replacing RL. And it's very general, can be used in other tasks such as simultaneous TTS and incremental parsing and so on and so forth. And more importantly, our work changed the view of simultaneous translation from largely out of reach by the current technology, or one of the hardest problems in AI, holy grails of AI, to something that is very quickly to be commercializable. So a lot of industry, a lot of, like Google, Facebook, Microsoft, and Baidu included, poured a lot of resources into this problem, and they deploy some really deployed systems in today's online meetings. A lot of meetings actually happened during the pandemic in an online virtual setting, just like this one, where you would see that audience from the worldwide would enjoy if you have would benefit if you have the service of automatic speech to text translation or something like that simultaneously, right? So I was invited to give the ACO keynote in 2019, and a year later we organized the first workshop on simultaneous translation, and another workshop, IWSLT, which is much more famous, much more popular than our workshop, started a shared task on simultaneous translation as well. So as a result, the number of researchers in simultaneous translation grew exponentially since 2018. But we also see a lot of active research areas because this is hardly from being done, right? There's a lot of open problems that left to be done, especially in two fields that I will detail in the rest of this talk. The first is adaptive translation policies. That is not just a fixed weight K, which is too kind of crude and too rigid, right? And the other is going all the way from speech to text or speech to speech even in a pipeline or even without a pipeline or in a direct approach. So that's something that we're going to talk in the next part of this talk. Now let's move towards adaptive translation policies. So as we said, weight K is too rigid or too kind of strict, and there is also a trade-off between latency and quality, where a smaller K is fast, low latency, but it could be too aggressive, you make a lot of mistakes, and a larger K could be too conservative, even though you get higher quality. So let's
江泽民对美国总统的发言表示遗憾。
So the last word is actually regret, even though you would anticipate it to be welcome in weight 3. This is because the model being trained on bytext, and bytext is like about 20 years old or 15 years old. In that time, the Chinese president is Jiang Zemin, and that time Jiang Zemin and other Chinese leaders were quite positive, as always, as it was the case to the West. So it's easy to learn an anticipation model based on those texts that the sentiment is likely to be welcome or gratitude or whatever. Not true for the current stage politics, but at least that's the model. That's too aggressive. With two words slower, like weight 5, you have enough time to hear the word regret, and you will not make this mistake, right? So then the question is, what's the optimal K? Well, it depends on your language pair. It also depends on your sentence pair, really. And more importantly, it really depends on this part of the sentence being very easy to guess and that part of the sentence being much harder to guess, and I would rather wait. So you want to adaptively change the K during the translation of one sentence. If you're confident, you go ahead. If you're not confident, I wait for more signals. So here's the first idea of adaptive policy that is based on weight K policies. So the idea is just train a bunch of weight K policies from K being 1 to 2 to 3 all the way to 9, let's say. And then let K dynamically change during decoding based on the confidence level. So the confidence level being the probability of the top one word of the current state. If it's greater than the threshold, say 0.5, then I say I'm confident enough. So I just write, which means I commit an output word. And after that, I decrease K. That means I switch to a more aggressive policy in the next state, right? And if not confident enough, I choose a read action, which is a wait action. That is, I want one more token from the source side. I can, encode one more source word. And after that, you would switch to a more slow or conservative policy, which is K++ or K increased by 1, right? And it's great, much better blue score at the same level of latency. The AL on the x-axis is just latency metric, being like how many words are you behind the source speaker. And we can see that it's much better than weight K, even though it's very simple idea of like ensemble of different weight Ks and dynamically choose which weight K to use. And you can see fixed weight 3 model, it makes wrong anticipations, offered wishes, even though it should be expressed simplicity. And our dynamic policy says and then wait a long time. Then we say express the most sincere, and then wait another time and simplicity too. And there's much better. But that's one idea. The other idea we had earlier was even better or a more beautiful idea. It's called policy as a model or read as a word. So now the wait token or the signal that you should pause and wait for more source input is treated as a target word. So in other words, this is a policy as model in the sense that there's only a single model. There's no like separate policy in the model, where the output could be a target word like meets or attends, in which case you would just write or commit these output words. It could also be a read token, in which case it's not really outputting anything. It's just wait for one more source word, like say a Bush president in Moscow. You say, oh, maybe I should wait until I heard with, right? Right? So that's a much better model, but it's harder to train because there's no ground truth signal. This kind of reinforcement learning problem. So you would use, but instead of using reinforcement learning, we would use imitation learning, which is much more controllable than reinforcement learning. So just to summarize on fixed and adaptive policies, the weight K model, the weight K policy we discussed in the first part was a simultaneous MT model, even though it could be also used with a full sentence translation model, which is called test time weight K. That is, only use weight K policy in decoding, but not use weight K model in training. Real genuine weight K means you both retrain weight K using the prefix to prefix objective instead of the sequence to sequence objective, but you also use weight K during decoding. So that's the genuine weight K or retrained weight K. But that's for fixed policies. For adaptive or dynamic policies, we have other work using RL and other methods. But our work is very simple and using, especially the one in blue, uses the heuristic rules to switch between different weight K policies. That's actually the most stable and most easy to use policy and works the best. Okay, so now we have covered text-to-text translation, but in real use cases, we want to do speech-to-speech, or at least speech-to-text, right? So during the pandemic, a lot of conferences, as I said, are held online, and they use a lot of speech-to-text simultaneous translation systems. At least the conferences that are held in China were all using those systems. So here we want to talk about two different approaches. One is the pipeline approach, where you have the ASR and MT and the MTTS pipelines, and the other the direct or end-to-end approaches. So first, the pipeline approach. So here you have a speech signal fed into streaming ASR, and then you got the source text stream, because all these three modules needs to be incremental, right? Because the whole thing is incremental or simultaneous. And then we talked about the text-to-text, and then finally you need a TTS system also to be incremental in order to produce target speech stream. You don't want to be using a the traditional full sentence text-to-speech system, right? So yeah, the one we just talked about is too simple. We should be doing the whole pipeline. And all these three modules need to be incremental, but this module, Stream ASR, is already widely known to be easily incremental. So a lot of services like on your phones have this, as Siri or iPhone dictation mode has this streaming ASR built in. So we will only need to focus on the incremental TTS mode, right? So this is also something that is new that that we need to incrementalize this TTS module. So I will not talk about any technical details, just play you some clips between human speech, full sentence TTS, and incremental TTS.
钱伟长想到上海来办学校是经过深思熟虑的。
That's human. Ground truth.
钱伟长想到上海来办学校是经过深思熟虑的。
That's full sentence TTS.
钱伟长想到上海来办学校是经过深思熟虑的。
You can hear maybe a tiny little bit difference between the incremental TTS and full sentence TTS, between the rhythm, between the pause pattern. But really, if you're not a native speaker, you probably cannot hear any difference at all. But this is generated on the fly, not after the end of the sentence, which can be used in the whole pipeline of simultaneous speech-to-speech translation. So then we went on to build the whole pipeline, but we got another problem. That is, a fixed weight K is really problematic in both slow and fast speeches. If you have a very slow speech, the thing is you would introduce unnatural pauses, here and here. This is because you would use, if you think of the target being synchronized with the source, then that means the source speech would control the pauses, the prosody, and the whatever intonation of the target speech, which is not necessarily the best thing to do, right? Because English prosody is very different from Chinese prosody. Where English speech have a pause doesn't mean that the corresponding position should have a pause on the Chinese side. It totally doesn't make sense, right? But a more important problem is actually fast speech. When the speaker speaks very fast, which is very common in the conference setting, you would accumulate more and more delays. You would lag behind more and more. That's common to a human interpreter. But here, also to a machine, that we would lag behind even more. And then the user will be out of sync if they use our service. That's very bad. You might say, we just changed the speech rate. We just play the speech faster. But actually, if you play it, only a little bit faster, the user suffer a lot. The user cannot understand very clearly. So the original speed is, the MOS score is 4. If you play it twice as fast, it's only 2. People cannot understand, right? You cannot play it too fast. So you have to use a more algorithmic way to a new idea. So our idea is called self-adaptive. That is to summarize whenever needed and to kind of elaborate when the speech is too slow, and to kind of catch up when you're lagging more behind. And it actually achieves much lower latency and higher accuracy quality than professional human interpreters in the UN. Even though this kind of evaluation is probably very unfair towards a human interpreter because it's evaluating using blue score, and blue score, doesn't like humans being too summarizing too much, because as I said, human interpreters only translate about 60% of the source material, and because in order to not lagging behind more and more, they have to summarize all the time, and this will be very much penalized by a blue score. So it turns out our work is so much better in terms of blue score, hugely better in terms of blue score, and also more importantly, it's 2.5 seconds faster than humans, less delays, less latency. Let's see the example.
Mr. Chairman, in all our work on conventional arms control, the international community is aided by civil society involvement. Civil society.
You can see the source, the human speech translation is very, very slow, lagging behind 5.5 seconds after the source speech. Why? This is because this 5.5 seconds, the human interpreter is still catching up with the previous sentence. She's still translating part of the previous sentence, and then she needs a bit of delay in hearing the current sentence. So the translation actually starts 5.5 seconds. That's around here, latency 5.5 seconds. Our work is much faster. This translation will start around 2 seconds.
Mr. Chairman, in all our work on conventional arms control, the international community is aided by civil society involvement. Civil society organization.
Now, of course, this pipeline approach is not ideal because in a pipeline approach, you always have a lot of error propagation from the ASR. The ASR is actually the majority of the source of the errors. For example, you have some code switching in Chinese, and you would be translating in a very funny way into English. So recovering from ASR errors is, especially like homophone errors, is a big problem, right? So we would propose to directly translate from speech to text or speech to speech. So how do we do it? And if we can do it, we can avoid error propagation and reduce the latency as well, because it's a single model instead of two. So GPU time, whatever CPU time is also faster that way. But the challenge is how do you segment the source speech and to apply it so that you can apply weight K policies. So in previous work, they would assume a fixed number of words within a certain number of speech frames. That's too bad. What we do is using two separate but synchronized decoders, one on streaming ASR and the other on simultaneous ST. But these two are kind of parallel in the sense that streaming ASR's output does not feed directly into simultaneous ST, otherwise it's pipeline, right? So simultaneous ST does translation directly from the speech signal, from the wave, doesn't depend on ASR's recognition. What it depends on is the ASR beam search, using the beam search to guide, but not feed as input to simultaneous ST. The beam search will just tell the ST, the simultaneous translation module, how many words I think there are in the speech, so that you can apply the weight K model, a weight K policy again. So that's the only key idea here. That is using ASR to tell the ST how many words there are and how fast you should be. So here's the more details, and I will not go into more details. So just we have two different sub-policies, the longest common prefix and the shortest hypothesis. The later is more aggressive because it's using the shortest hypothesis in the beam search. The other is using the common prefix, longest common prefix in the beam search being more conservative. And I will just show you two examples, one from English to Chinese, the other from English to German. And here, the first one from English to Chinese.
But then 2 weeks later, she called me, she said, "Did you know that if you moved to the United States, you could change your name and gender marker?"
So here we notice a few problems. In the ASR system, which is here, United States is recognized as states. The United States is recognized as states. And as a result, in the cascaded system, you would have 国家, which means country, instead of USA, which means instead of USA, right? In our direct system, which are these four lines, you will always have 美国, because it's not affected by the errors in the ASR. It does the job of translation from speech signal directly and separately from the ASR. That's the first thing. And there's another ASR, which is now shown here, which recognizes the United States as united. It's even worse because the translation would then take it to Manlian, which is Manchester United, right? And the other thing is that our translation policy, our direct policies are faster than cascade, especially for the SH policies, because it doesn't depend on the ASR output. You can see again.
But then 2 weeks later, she called me, she said,
it's fast.
"Did you know that if you moved to the
faster than
United
cascade.
States, you could change your name and gender marker?"
Now, English to German, here also there's an ASR error.
Can I be honest? I don't love that question.
Can I be honest? And this honest is recognized as on this by the ASR. Can I be honest? It's actually, can I be honest, even though they really, really sound very close to me. I mean, I cannot differentiate them as a non-native speaker. And if you use cascaded system, then you got doomed because on this becomes Dasein instead of honest, right? And our system, being direct translation, can get it correctly, right? And you can also notice that it's much faster than the cascade system. Like the Ich liebe diese Frage part is translated much faster.
Can I be honest? I don't love that question.
See, it's much faster, right? Now, the final module is actually more like a bonus track, which we will talk about multimodal models for simultaneous translation. And here's something that may be connecting back to CVPR, because finally we'll be using vision. But it has two subparts. The first part is actually speech and text multimodal. It doesn't have any vision at all from my group. And the other is vision-aided simultaneous translation from Lucia Spatia's group, which is completely not my work. It's totally independent of my work. It's a courtesy that we can use her slides here. So here, first, multimodal pre-training for speech translation. So the specific, this is a paper that will appear at ICML this summer, but the specific topic here is direct full-sentence speech-to-text translation. Even though the same technique can be used, and we actually have done that, to direct simultaneous speech-to-text translation, and can similarly improve simultaneous speech-to-text translation, just like the previous module. The limitations of direct speech translation or speech-to-text translation, even though it's a very hot problem right now, is that you lack the large-scale parallel speech translation data. You don't have that much data that is, source speech and target translation, like source English and Chinese text. You don't have that much data like that because it's unnatural. But you have lots of data that is, ASR, English speech, English transcription, and MT data, which is English transcription and Chinese translation, right? So you have this triangulation thing, right? Because at each node, you have tons of data, even a lot of monolingual data, like non-parallel data, like source speech alone, or transcription alone, like you can use BERT, and target translation alone, you can also use BERT and so on. And then these two lines, line segments are also abundant, like this ASR direction is abundant. This translation direction is also abundant. It's just this, from source speech to target translation directly, that's scarce, right? But we can go, go on a detour and use all these different modalities of translation, of parallel text, of training corpora. Then we can have a lot more data, tens or 100 times more than direct speech to target translation alone, right? So we propose a kind of a unified representation encoding that can encode all these different modalities and all these different kind of data. And it's the first speech and text multimodal pre-training. So it can improve speech to text translation quality over the cascaded system, for example. So here's the source, which is very fast speech.
Those are their expectations of who you are, not yours.
Even I cannot hear it clearly. Those are their expectations of who you are, comma, which is not shown on ASR, comma here, not yours, right? And ASR would say those are their expectation, this there and this there. It's hard to differentiate, especially in a streaming ASR setting, right? Especially in the streaming to do of who you are, not yours. And then the translation is, of course, totally wrong. But our direct translation system is much, much better. It's actually perfect translation. Second example is heavily accented speech.
She is not welcomed, neither by father nor by mother.
Neither by father nor by mother, and it's recognized as nar by mother by the ASR. And as a result, the translation is nar by mother. That's totally hilarious. Our system is much better than that, being direct translation. And finally, there's something that connects back to CVPR, that's the vision-aided simultaneous translation. As we all know, if you are deploying your system in a conference setting, you have slides, you have the speaker's gestures, you have a lot of non-verbal language, non-verbal information like the eyebrows, the facial expression. You have all these kinds of visual information that you can encode to help your simultaneous translation system. In fact, Lucia Spatia's group have explored that a lot. And here's the example on English to, say, French or German or Spanish simultaneous translation, where you need to anticipate a lot of things, especially in weight 1. They actually use weight 1 because 1 is too small for the weight. You have to be really in sync with this source speech. Only one word behind. But the word order is actually different between English and French, and also between these different languages. And also you need gender markings on the non-English European languages like French, German, Spanish, Russian, Italian, whatever, right? So here's the example. So if you say a white cat in English, and if you translate in weight 1, that is only one word behind into French, then you got a problem. So you say hearing then you say on. Then you hear white, what you should say? Well, you haven't seen the cat yet. You have to anticipate. And how can you be able to anticipate? It's impossible, right? You haven't. This could be dog, this could be man, this could be whatever, now it could be. But if you have the picture or video or whatever, visual information before you, you can say, oh, you know what? I can say it's a chat, right? And also remember the gender marking is actually the first pronoun, the un or une, or in Spanish una or uno, in Italian as well. So that also needs to be decided depending on the noun here. It's a cat or a dog or a bird, use different, or a woman or a man is a different pronoun, right? So that's completely impossible without the image, without the visual information. See, here's another example from weight 1, from German to English to German. The source sentence is a young brunette woman, and the picture is like this. But if you don't have the picture, then you would have, ein, which is masculine, which is not true here. Younger is also masculine. Brunette Frau, that's wrong. But if you have, so this is simultaneous translation, because if you have the whole sentence, that's not a problem. So we're only talking about a problem which only happens in simultaneous translation, where you have to anticipate, right? You don't see the brunette woman yet. You don't know it's actually female, it's actually feminine. You should use eine junge brunette Frau. But because you have the image, you can easily anticipate under weight 1 setting, under the extreme latency setting, extreme low latency setting. Same thing for English to French. And here, it's more like this example here, black and white bird. But you don't know what kind of animal, what kind of even object it is. But you have to say it in French because it's like un casa grande. It's not instead of a big house. So you have to say un chien, un oiseau. In the correct version, un oiseau noir et blanc. But you don't know, so you would anticipate randomly in a standard weight case system, a standard weight 1 system, without seeing the image. You would say un chien or un chat or whatever, right? Or maybe une or something. Like you can make all kinds of mistakes, right? So, but with the image, you say, oh, un oiseau. Even if you only have heard a black, a black what? Completely not sure, but it's un oiseau. Noir et blanc. So with the image, you can do a lot better using a lot smaller k, using this extreme small k of k weight 1, which is impossible without the image. So that's 2 great examples from Lucia's group. Okay, so I hope I've told you some stories that you enjoyed, and in particular, we invented a prefix to prefix framework, especially the weight k policy, which is very easy and effective, and turns simultaneous translation from obscurity to a hot research topic, and also a commercializable direction. And the adaptive policy is more kind of dynamic and more flexible than the weight k policy, and can improve latency and quality. And we're also making the first steps towards simultaneous speech-to-speech pipeline approach, which can surpass professional simultaneous interpreters in the United Nations, even though it's a very unfair evaluation in both latency and quality. And we're also making steps towards direct, that means end-to-end, not pipelined, simultaneous speech-to-text translation systems. And it can avoid error propagation from ASR and reduces latency. And here, our speech translation is guided by, but not using input from, streaming ASR, the beam search of streaming ASR. And finally, we address the data scarcity problem for speech translation by pre-training using multimodal, unified representation. And at the end, I think I connected with you guys by showing that vision actually can help you anticipate in simultaneous translation. These examples are, the image is useless if you just do machine translation, because the whole sentence is already there. So you wouldn't make this kind of example, this kind of mistake at all. This kind of mistakes only happens during simultaneous translation, where you don't have the full sentencing information. Then you need the help from the image. Yeah. So I hope that this is the final bit of work that is not from my group, helps my talk to connect with you guys. So I would like to thank my students, co-authors, and collaborators again, and I would like to thank you very much in a simultaneous setting, which is weight 2. Actually, this is the output from our real system. It's not fake. Thank you very much, and I would like to take some questions. Thank you.